Hello, general chemistry students. This is the fourth video in week 12, and we will be doing some equilibrium calculation problems. And so a bit of a warning before you get into this video, we are going to be working on a lot of problems, and so you may want to stop the video at any time and work through it on your own, because I may be going pretty quickly through this. So stop the video at your leisure to work on the problems. Really important that you work on these problems with me as we go through this video, because these will be things that you'll have to do when you start doing your checkpoints. Alright, so this video is going to be quite lengthy because we're going to be really focusing on how do we do these equilibrium problems. Alright, so a few things. By the end of this video, you'll be able to use equilibrium constants in order to find those equilibrium concentrations. At the same time, you'll be able to predict the direction of a reaction progress. So we're going to introduce something else called the reaction quotient. We're also going to use that quadratic equation that you put away in your brain so many years ago, and we're going to use that to solve for equilibrium concentrations. And then we're going to bring in something that you'll really like, and that's the simplified approximation. And so we're going to determine when can we use it when we're doing these equilibrium concentrations. And so something that you may have to do on your own, and that's practice, practice, practice. We really need to practice these equilibrium problems. All right, so let's get started. So this is our first problem. We have an equilibrium concentration of our COF2 and our CF4, and we're going to find the equilibrium concentration of CO2. All right, so what we're given is you're given the reaction and a Kc. All right, so the Kc is 2 at 1,000 degrees. And you're given the concentrations of all but one of these. Okay, so we have our reaction. We have 2 COF2 forms CO2 and CF4. So we're given the reactant concentration at equilibrium, and we're given one of the products at equilibrium, and we need to find what the equilibrium concentration is of one of the products. All right, so what we can do is we can calculate the missing concentration by using the equilibrium constant expression. All right, so these are the things we know, and what we're going to find out is the concentration of CO2. And we know that the equilibrium constant is our CO2 times CF4 divided by COF2 squared. Okay, so that's our expression, and we can really insert all those numbers except for CO2. So we can just solve for CO2 given all of those numbers. All right, and so we're going to solve for the equilibrium concentration by substituting in what we know. Okay, so first off, let's rearrange this equation to solve for CO2. All right, so we can do that, and CO2 is equal to our Kc times COF2 squared over CF4. Okay, so we can just put in our numbers, and we come up with 1.1 molar. All right, so the next thing to do, and we should always do this when we do problems, is let's check ourselves. Does this number make sense? All right, so let's substitute back and see if it agrees with the value. Okay, so we take our concentrations of 1.1 times 0.118 divided by 0.255 squared, and we get 2. All right, so it works out. So this number does make sense to us because we get back our original equilibrium constant value. All right, so let's work on another problem. So here we have a sample of PCl5, and we're going to form PCl3 and chlorine gas. Okay, so what we're given is we know the volume of the container we place it in, so it's a 0.5 liter container, and we know the moles at equilibrium of PCl3 and Cl2. Okay, so we need to determine what the equilibrium concentration of our reactant is given our Kc. Okay, so Kc means concentration, so we're going to use our moles and divide by our volume to give us concentration. All right, so when we do that, we come up with our values of 0.406 for both PCl3 and Cl2. All right, so our Kc expression is our products divided by our reactant. Right, so we can solve for what we need to solve for by just rearranging the equation. And so then we can say that PCl5 is equal to our PCl3 times our chlorine divided by our Kc. Okay, so we work that out, we put in our numbers that we calculated for our concentration and divide by our given Kc. Right, so our concentration of PCl5 is 2.6 molar. All right, so now we're going to switch gears a little bit and we're going to talk about how do we know the reaction progress in, what I mean by that is, what is the direction the reaction is going? Okay, so we're going to bring in something called the reaction quotient, and the reaction quotient is Q. All right, so we can first decide on which direction the reaction is going by looking at the reaction quotient. Okay, so the reaction quotient has the same expression as K. The only thing here is Q is not at equilibrium. Okay, so Q is not at equilibrium. And so once we calculate Q, so for any point on that reaction, we can compare it to K and determine what is the direction of the reaction. Okay, so we can first decide on the direction the reaction will proceed by comparing those values, Q and K. And then we can define the changes of all materials in terms of some value X. So X is the change, is positive for materials on the side of the reaction that it's going towards, and negative for the materials on the side that it's going away from. So imagine a reaction that's going forward. We would have positive products and negative reactants. On the flip side, if we were going in the reverse reaction, we would have negative products and positive reactants, okay? And then we can solve for X, okay? And we'll solve for X either using the quadratic formula or we'll simplify using our approximation that I told you about earlier. All right, so let's take this reaction. Iodine and chlorine form 2ICl. We have a Kp associated with it of 81.9. If we have initial partial pressures of 0.1 atm, find those equilibrium concentrations. Okay, so we're going to set up our ice table. Remember, our ice table is really just a way to keep us organized when we're doing these equilibrium concentrations. So we define what we have initially, and so we're given the pressures, of iodine and chlorine, and of course in the beginning we have no product. All right, and so we can look at what Q is and define we have all 0.1 atm. Okay, so we can look at what Q is and we can see, well, Q is 1. All right, and then we can compare that to our Kp. So Q is less than K. So what's happening here then is the reaction is proceeding forward. All right, it's going from reactants to product because eventually we want to reach the Kp of 81.9. Okay, so now we've just decided that this reaction is going to proceed forward. Okay, so now what we can do is we can start filling in those positive and negatives. So our change here for our reactants will be negative, and our change for our product is going to be positive. But notice I put a positive 2x here, and that's because that is the stoichiometric coefficient. Okay, so those x's, you really need to keep in mind those stoichiometric coefficients. All right, so what do we have at equilibrium? Well, so because our reactants are going away, so we'll be 0.1 minus x each, and our product is coming in, so we'll 0.1 plus 2x. We can put that into our expression for our Kp so that we can solve for x. All right, and so here we can take the square root of 81.9, and that's equal to this value, 0.1 plus 2x divided by 0.1 minus x. All right, and so here we're just rearranging the equation. So we'll multiply times our 0.1 minus x, and that's equal to 0.1 plus 2x. All right, and when we rearrange some a little bit further, we have a value of the square root of 81.9 times 0.1 minus 0.1, and that's equal to 2x plus 81.9, the square root of 81.9 times x. So essentially what we've done is we've rearranged this equation so much that we don't have to use the quadratic equation here, okay? And so when we do all of that, we can solve for x, okay? So we've sort of circumvented the whole quadratic equation here by just rearranging the equation. And so we get x is equal to 0.0729. And when you do that, you always have to look back to see what did you define as x. So we defined x as the change. So in the end, we would take 0.1 minus 0.0729 to find what those equilibrium concentrations are. All right, so we can substitute those into our ICE table, and we can calculate our concentrations at equilibrium, and we come up with 0.027 each and 0.246 at equilibrium. All right, and so now we want to check ourselves. Okay, so we want to check ourselves to make sure that we have the correct concentrations, and the easiest way to do that is just put it back into the Kp expressions and see if you get something that looks like your original Kp. All right, so the Kp calculated is equal to Kp given within those significant figures. So we are good, all right? We have calculated the correct concentrations, and that error really comes from our rounding. So we don't have to worry, we just have to make sure that it's really close. Okay, so now we're going to introduce ourselves back with the quadratic equation. So remember we had that minus x and the positive 2x. Now, there are some times when we have to use x, or sorry, you have to solve for x using the quadratic equation. All right, so we're given this reaction of iodine forms two iodine atoms. And the value of Kc is given as 3.76 times 10 to the minus 5 at 1,000 K. So if we have 1 mole of iodine and it's placed in a 2-liter flask and heated, what will be the equilibrium concentration of iodine and iodine atom? Okay, so we're going to use the quadratic formula here to solve for x. Okay, so a little bit of a review. What the first thing you have to do when you solve for the quadratic formula is get it into this form. All right, it has to be in this form of ax squared plus bx plus c. Okay, then you can define what those letters are, because a is going to be the part that's part of x squared, b is going to be the part that's of just the x, and c is going to be just a number, right? And then to solve for x, there's going to be two values because this is the quadratic equation. You're going to have a positive number and a negative number. Okay, you want a concentration that's positive, so you get rid of the negative number and you keep the positive number. Okay, so it's going to be minus b plus or minus, because there's two values, so you'll take the value of plus and then you'll take the value of minus, and then b squared minus 4ac, so the square root of that, divided by 2a. Okay, and you're going to get two values. Keep the positive, throw out the negative. All right, so initially we're going to have a concentration of iodine atom is 0, and the reaction is going to proceed forward. All right, so let's put in our change. Because it's proceeding forward, we have iodine as minus x and iodine atom as plus 2x, coming from the stoichiometric coefficient of 2. So at equilibrium, we're going to have 0.5 minus x, and we're going to form 2x. So we can put in our expressions for Kc, and so we have 2x squared over 0.5 minus x. All right, and so what we come up with is this value is equal to 4x squared. All right, and so we can substitute in to our quadratic equation by defining what is b, what is a, and what is c. So b here is 3.76 times 10 to the minus 5. And A here is 4, and C here is minus 1.88 times 10 to the minus 5. And we're going to divide by 2a, which is 2 times 4. All right, and when we solve for that, remember we get two roots, but we throw out the negative one and we keep the positive. So the positive one here is 0.00216. All right, so we arrange this quadratic formula into, like we saw before, so we have A, B, and C. All right, so those are the values we use for A, B, and C. All right, so we solve for X. Now what we want to do is we want to find those equilibrium concentrations. So we take our 0.5 minus our X to give us our equilibrium concentration of iodine. And then we take 2 times x to give us our equilibrium concentration of iodine atom. Okay, always good to check. So we take our concentrations that we calculated, and so we'll take 0.00432 and square it, divide by 0.498, and we get 3.75 times 10 to the minus 5, really close to our Kc that we are given up here. Okay, so the check is good. We have good concentrations here, good equilibrium concentrations. All right, so the moment you've all been waiting for, the quadratic equation is a pain in the butt. Are there times when we can just approximate in order to simplify the math? And the answer is yes, but we have to know when to do it. So we can usually simplify the math when the equilibrium constant is really small. And the position of the equilibrium favors the reactants, all right? So a small equilibrium constant, and the equilibrium is going to favor the reactants. So K less than 1, so a really small equilibrium constant, we can simplify. Or for relatively large initial concentrations. Okay, so either a really, really small equilibrium constant or large concentrations, because they're going to balance each other out. And here we're going to assume that the reaction is always moving forward. Okay, so how can we check? So we're going to check our approximation by comparing the value we calculate to what the initial concentration is. And if that approximate is less than 5%, we're going to say it's good. All right, so we have an approximate x that we calculated using our approximation, and I'll show you that in just a bit, divided by our initial concentration times 100. If that's less than 5, go ahead, you're good. All right, so let's do an example. So we have this reaction of H2S forming 2H2 plus S2 gas. We're given a Kc, and we have our reaction in a flask, and we're given the initial concentration of H2S. We're going to find those equilibrium concentrations. All right, so here we go. So we know that the reaction is proceeding forward because Q is 0 because we initially don't have any products. All right, and from stoichiometry, our H2S is going to decrease by minus 2x. Our H2 is going to increase by positive 2x, and our S2 is going to increase by positive x. And I also want to point out here that we have a really, really small Kc, right? So we're going to try doing this approximation here. All right, so at equilibrium, we're going to have our initial concentration minus 2x, and H2 is going to increase by 2x, and our S2 is going to increase by x. So we're going to solve for x. Also, I want to point out that we have 1.25 times 10 to the minus 4 moles in a 0.5 liter flask. That's where I got this number, 2.5 times 10 to the minus 4, in case you were concerned with that. All right, so let's put it into our Kc expression. So we have 2x squared times x divided by 2.5 times 10 to the minus 4 minus 2x, and we're going to square that. All right, and so see what I just did? I took out that minus 2x. So here we're going to assume that x is small so that we can approximate. So this is the key here, because if you take out that minus 2x, you don't have to use the quadratic equation. So I'm going to take out that minus 2x. I'm going to see, was I correct that I could approximate? Okay, so that simplifies it so that we don't have to do the quadratic equation. We can simply solve for x here. All right, and when we do that, we get 1.67 times 10 to the minus 7, and that's equal to 4x cubed over 6.28 times 10 to the minus 8. So essentially what I've done is I put these together and I've squared that value. All right, so now we can just multiply times 6.25 times 10 to the minus 8, divide by 4, and take the cube root. All right, so to solve for x, we're going to multiply those values, divide by 4, and take the cube root of that to solve for x, and we get 1.38 times 10 to the minus 5. All right, so now let's solve for those equilibrium concentrations. Well, first let's check our approximation. So we have 1.38 times 10 to the minus 5 divided by 2.5 times 10 to the minus 4 times 100. All right, so this was our initial concentration. This is what we're solving for x. Oh no, it's greater than 5%. What we're going to do is, so if the approximation is invalid, we're going to substitute our current x into Kc, and where it was subtracted and resolve for x new. Okay, so so what we're going to do here is we're going to circumvent that quadratic equation just a little bit. So we're going to put in that the x that we just calculated to solve for, so that's going to be just this minus 2x. So we're putting it right there and then solving for x again. Okay, and when we do that, we come up with another value of 1.27 times 10 to the minus 5. Okay, so now what? All right, so now our x current is 1.27 times 10 to the minus 5. And we can put that in again solving for x, and now we have 1.28 times 10 to the minus 5. It hasn't changed very much now. So what we're saying here is that if x new is the same number you have arrived at, it's your best approximation. Okay, so what we're saying here is that either using 1.27 times 10 to the minus 5 or 1.28 times 10 to the minus 5, both of those are your best approximation. Okay, so now let's put in that value to find our equilibrium concentrations. All right, so our equilibrium concentration of H2S is 2.2 times 10 to the minus 4. H2 is 2.56 times 10 to the minus 5. And our concentration of S2 is 1.28 times 10 to the minus 5. That's the x that we solved for. That's our best approximation. All right, so let's check ourselves. So we used our best approximation here, because remember the first approximation was too large. And then we tried it 2 more times and we saw that the next 2 times that approximation didn't change, so we could use it. So now we want to check it. We want to make sure that we have the right concentrations at equilibrium by substituting in those concentrations and comparing what we get to what we're given. Okay, so we take our concentrations, so 2.56 times 10 to the minus 5 and square it, and 1.28 times 10 to the minus 5, divide by 2.24 times 10 to the minus 4 and square it. We get 1.67 times 10 to the minus 7, which looks to me awfully like what we're given in the original problem. All right, so we're good. Circumventing the quadratic equation. All right, so now what we're doing is we are increasing the concentration here. So remember, our approximations are valid if you have a low low equilibrium constant, all right, and we do, or high concentration. So now we're putting 1 mole of iodine into a 2-liter flask, so we're increasing that concentration. All right, so let's see what we can do here. So we set up the Kc expression. We have 2x squared over 0.5 minus x. We're going to get rid of that minus x because we're going to assume it's small. And we're going to say the 2x squared over 0.5. So this simplifies it very nicely for us, where we can just simply solve for x. All right, so we can divide by 4, take the square root, and we get 2.17 times 10 to the minus 3. All right, so let's check our approximation. So that 2.17 times 10 to the minus 3 divided by our original concentration times 100, we get 0.434%. That's a lot less than 5%. So here we can say that our approximation is valid. We don't have to go through that iterative process to find a better approximation. All right, so we can just use X as it is. All right, so now we know X, we can solve for those equilibrium concentrations. So here iodine is 0.498 molar, and our iodine atom is 0.00434 molar. All right, so the next step is we want to check ourselves. So we take our concentrations that we calculated and put it into the Kc expression. So we have 0.00434 squared divided by iodine, and we get 3.78 times 10 to the minus 5. Oh my gosh, it's really close to what we're given in the problem. So here our approximation is valid. We're good. No extra steps. All right, so let's do another practice problem. So we have this reaction again, our N2O4 forms 2NO2. We have a value of Kc. We have our initial concentration of our N2O4, which is our reactant, and we're going to calculate the equilibrium concentrations of our N2O4 and our NO2. Okay, so we're given an initial concentration and we're given an equilibrium constant. All right, so let's set up our ice table. So what we know initially is that we have 0.0125 of the reactant and no product. We're going to change by minus x and plus 2x, right? Because that's our stoichiometric coefficient. And so at equilibrium, all right, that's not good right there. At equilibrium, we have 0.0125 minus x and 2x for NO2. Okay, so now what we want to do is we want to put that into the Kc expression. So we have 2x squared over 0.0125 minus x. Let's assume x is small. We're going to approximate here, and that simplifies to 0.0125. And now we can just simply solve for x. All right, and so we're going to compare two examples with our approximation and without our approximation. So with our approximation, again, we can simply solve for x here, and we get 1.83 times 10 to the minus 4. Again, we're going to check that value divided by our original concentration times 100, and we get something that's less than 5%. Okay, perfect. So we're saying that approximation is good, but what would it be if we didn't approximate? You know, we go through that quadratic equation that I showed you. Okay, so again, we can set this up and we can solve for the form of the quadratic equation where we have our A, we have our B, and we have our C. Okay, so we put that in the form of the quadratic equation. Again, you're going to get two values. One is negative, one is positive. Keep the positive. And here, without approximation, we have 1.82 times 10 to the minus 4. All right, that looks really close to with our approximation. All right, looks really close. So let's go through and calculate the equilibrium concentrations. So for N2O4, we have 0.0123 molar at equilibrium, and for their NO2, we have 3.66 times 10 to the minus 4 molar at equilibrium. All right, always good to check yourself out. So you take your concentration of NO2 squared divided by your concentration of N2O4. Is it the Kc? Is it the Kc that you're given? And it sure is. So this, even with the approximation, it's good. So we showed that with the approximation, without the approximation, they were essentially the same number. And then when after we found our equilibrium concentrations and put it back into the Kc expression, we find that our Kc's match. So we're good. All right, so that's the end of this video, video 4, when we were doing practice equilibrium calculations. Thank you.